Good evening, everyone. My name is Renu Raman Sahu, and today we will be revising the questions and answers we have been discussing in all the past weeks. So, let us start with the first session, the questions and answers. So, the first question is it like first question we have to answer true or false? So, is it important to understand the exact thermal profile of a flame in order to use it for cooking? So, this is certainly false because for certain applications we don't have to exactly know what is the thermal profile. As long as we know that it is getting heated up and it is hot enough to for cooking, we don't have to know the exactly what is the thermal profile. A model is useful only if it can predict data over a full range of experimental conditions. So this need not be true. Why it need not be true? Because uh, it can even if it can predict data over some range of the experimental conditions, then it is good enough for that particular range. So for example, if a model predicts something uh, in the range of experimental conditions which is useful for our daily day-to-day life, then we don't have to bother about what is uh, what would be the data in the other regions of that region of interest. So this statement is false. The third question is empirical models are useful even if the underlying science is not understood. This is true. Why? Because empirical models help us to predict a given data even if we don't know the underlying science. So the model will help us to determine what would be the data for a certain range. So they are useful. There are no instances where theoretical prediction has been made even before experiment has been conducted. This is false because there are many experimental conditions or many phenomena have been predicted by means of theory. So first, for example, certain particles, for example, Higgs boson, they were theoretically predicted much before then they were experimentally demonstrated, and Bose-Einstein condensate is another example. And uh, theoretical prediction can go first theoretical prediction, then experimental, or first experimental, then theoretical uh, understanding of it. So they can go hand in hand and not in a particular order. For all materials, as temperature increases, electrical resistance increases. So this is not true because there are certain materials for which the electrical resistance decreases if we raise the temperature. For example, semiconductors. In semiconductors, if you raise the temperature, then the electrical resistance will decrease. The two ends A and B of a long metal bar are kept at two different temperatures, 60 and 100 degrees Celsius respectively. A 4 probe measurement shows that dash at the both end is dash. Okay, so the ionic conductivity at both the ends. So remember that it is a metal, and a metal has and with four probe measurements, what we check for is the conductivity or resistivity, because 1 by rho is resistivity. So conductivity can come from different sources, like for example electrons can contribute to it, and electron can contribute to it, ions can contribute to it, and other charged spaces can also contribute to it. But in a metal, the ions are at a particular location, they don't move much, and majority of the conduction they come from the electrons. And now electrons, if they are at different temperatures, their mobility will be different. So particularly if you remember the uh, conductivity, n e square tau over m. So the conduct and this tau, it depends upon v square average, which further depends upon the temperature. So if they are dependent on so conductivity depends on temperature. So if, and this is electrons, this is for electronic conductivity, electronic conductivity. So at different temperatures sigma will be different, so electrical conductivity will be different, but the ionic conductivity, they will be the same, because the conductivity from the ions is negligible, it is almost zero, whatever the temperature may be. Three states of material are solid, liquid and gas. Among various properties of material, yeah, solids can have the mechanical properties, that's true, because for a solid we can do this stress strain diagram as shown in this figure. Gas can have mechanical properties. So the mechanical properties of, by mechanical properties we mean properties like stress, strain, what is the Young's modulus, what is the elastic limit and so on. So gas can have fluidic properties, not mechanical properties. So liquid can have electrical properties. That is true, because by electrical properties we mean conductivity, resistance and so on. So liquid do have these electrical properties. Gas can have thermal properties, yes, because like what are the thermal properties? Thermal properties are like the pressure, the temperature of the gas, the flow of temperature, pressure and uh, the other thermal properties include thermal conductivity and so on. So gas do have the thermal properties. Most of the gas, like for gases properties, for example, what is the pressure? Pressure, it from kinetic theory. So gas follow this law, PV equal to nRT, and RT. This is a, this pressure, volume, all these are temperature dependent properties. So they do have thermal properties. The resistance of a metal filament is used in a bulb goes up with temperature. That is true, because they have a positive coefficient of resistivity, positive thermal coefficient of resistivity. So it is true. A bimetallic strip in an electric iron box works as a, so a bimetallic strip, what it has is A and B is a bimetallic it is a strip with two components A and B, and they both have different coefficient of thermal uh, resistivity, and because of that they different coefficient of thermal expansion as well. So when this is heated, they will expand in different ratios, and that is why they will bend upon heating. So this can be used as a temperature regulator, or a temperature regulator and a switch. It cannot be used as a temperature indicator, because uh, it can be used as a temperature indicator as well, because it can regulate the temperature, what is the current. So depending on what is the current, what is the temperature at which this bimetallic strip is straight, it's T naught. Based on that we can get, so we'll have what is the bending or the curvature of it, and based on that curvature we can find what is the temperature. So but we need to have, so there needs to be this calibration done beforehand. Which material property is responsible for the formation of ferric oxide in an iron pillar? So formation of ferric oxide is just an oxidation, it is an oxidation phenomena, and since it is an oxidation phenomenon, as you can see in this reaction, Fe, it has to form a ferric ion Fe3 plus, and it gives 3 electrons, and these 3 electrons has to they will be taken up by the oxygen to form oxide, and ferric oxide will be forming. So this is a chemical reaction, and in chemical reactions are characterized by the chemical reactions are characterized by the motion of charges, or the transfer of charges between atomic spaces. thermal expansion coefficient of an ionic material is impacted by its electrical conductivity. So thermal expansion coefficient of an ionic material, it is so these are independent thing. Electrical conductivity has nothing to do with ionic material. The thermal coefficient of and thermal expansion coefficient of ionic material. The reason of thermal expansion is completely different. It is because of the equilibrium lattice vibration, the mean position of the equilibrium lattice separation or lattice spacing. And electrical conductivity is a totally different relation. So these are not impacted by each other. So the answer is false. An example of a material with excellent thermal conductivity but poor electronic conductivity. So, excellent thermal conductivity is diamond, because diamond has there because of so iron, graphite, and aluminum. They are very good in electrical conduction. Whereas diamond, because it has a tetravalent bonds, all the four of its valence electrons are used up in bonding. So they have a very poor electronic conductivity. On the other hand, because diamond is well bonded with all other four carbons, it is a very excellent conductor of thermal heat because of this bonding. So there are phonon modes which will get heated up quickly and they can transfer the heat. Materials with negative thermal coefficient can be they can used for negative thermal coefficient means if you heat the material it will start shrinking. Those kind of material are called heat shrink materials as well, and they can be used for sealing the joint. For example, if you like tie that negative thermal expansion coefficient material around a joint or a brokerage, and then you heat it, then it will shrink and it will tighten the knot or tighten whatever the kind of joining knot you have put in. The sealing material, so it is used for sealing the joint between two wires, and it can be used as a heat shrink material. And a washer to seal again leaks in joints between tubes as temperature increases. So this cannot be used as a washer. A sealing material that will seal the mouth of a packet by heating it. So this is true because if you heat it, it will contract, and on contraction it will seal the mouth of the packet. The energy versus distance curve used to describe thermal expansion in a material is a combination of so the energy versus distance curve, it is the correct answer is it it has to be for example, let us say in a material, for example, let's say sodium chloride. This material, for example, the sodium has to first get ionized, then chlorine has to acquire that electron. So ionization energy and electron affinity are, these are like the constants, and both of them they will contribute to the process of increasing the potential energy by some constant value, increasing or decreasing by some constant value. Now the Coulombic energy and the electron cloud repulsion, they are, Coulombic energy is what? Coulombic energy is the attraction between these two ions, and attraction between the two ions is given by this Coulomb, Coulombic force E square by 4 pi epsilon naught r. And there is this there is another term where this energy goes as B over r to the power 10, which is a very rapid increase of the energy because of the cloud, electron cloud repulsion energy, because this is the energy given by the repulsion of the electron clouds. So these are the contributor to describe the thermal expansion of a material. If the energy versus distance curve is of symmetric nature, then the mean atomic position, so if the energy versus distance curve, if it is symmetric, then the mean atomic position will not change, because as you can see in this parabolic diagram, as you increase the energy, so this is the energy and this is the distance. So as you increase the energy, you see that you are not changing the mean position, it is always at the center. On the other hand, since the energy versus distance curve is So this is energy on x-axis and energy on y-axis, and this is energy on y-axis and position on x-axis. So you see that the mean position is shifting towards right. So if it is symmetric, then the mean atomic position will remain unchanged. Now let's discuss about the questions and answers of session 2. So in lithium ion batteries, the charge carriers are electrons as well as ions. So that is true, because there is a phenomena of charge separation going on where the electrons and ions both are migrating. So that is true. Resistivity is an extensive property. Resistivity, see, the resistance is given as rho L by A, where rho is an intensive properties. It depends only on material and not upon its dimensions. Since it doesn't depend on the dimensions of the material, it is an extensive property. It is an intensive property. So the fact that resistivity is an extensive property is false. For a resistor, resistance and impedance are the same. That is true, because Z is equal to R in case of a resistor. A capacitor always display very low impedance in response to low AC signals. So the impedance of a capacitance is given as minus I upon omega C. If the frequency is low, then Z will be very high, because Z frequency is in the denominator. So that is why this statement is false. In a simple cubic structure, larger atoms result in smaller fraction of vacant space. So that is false, because even if uh, what is the fraction of uh, so irrespective of what is the size of the atoms, the fraction of vacant space is similar in the simple cubic structure. The ionic and electric conductivity can be accurately measured by two probe method. So that is false, because in two probe method we have to come across the contacts, and that makes the life difficult, and we have to lose out on certain material as well. Whereas if we measure what is the conductivity across the device by means of a wire, then we can get so it would be a 4 probe method, because two of the probe will be used to send current, and the other two probe will be used as a the other two methods will be used as a other two probe will be used as a voltage detector. In a 4 probe measurement, the distance of an ideal voltmeter which is connected in parallel to the sample is, it has to be, ideally that resistance has to be infinite. Why? Because the so when it is infinite, it will draw very less amount of current. When it will draw less amount of current, then it will the fall of the potential will be close to the real value, or else it will, the potential drop will be a little bit uh, less, because majority of the majority of the electrons will go through the voltmeter itself. That is why in principle we want no electrons to pass through the voltmeter, and in that case the resistance of the ideal voltmeter is infinite. The free electron gas of a metal consists of the valence electrons released by each atom which roam inside the solid. The motherboard of a computer conducts electricity and all of the components attached to it. The yeah, the motherboard, it increases The conducting species in the motherboard of electrons are, they can be electrons, uh, electrons because there are wirings which can flow in that. That can be ions, for example, in the battery UPS or something, and they can be holes when there are certain semiconductors used. It is not protons because protons are boundly they are very bound to the nucleus, and protons do not participate in conduction of electricity in the material. The common AC impedance equivalent circuit elements, the elements where there is a phase difference between current and voltage, is nothing but capacitance and inductance, because they have an iota factor in it and they are out of phase by 90 degree. What will be the approximate packing fraction of an atom of an element having platinum atomic number 84? Okay, so the most common form of the atomic number having element, or the atomic number 84 element is polonium, and it is found in its most common form as alpha polonium. So alpha polonium to simple cubic, and uh, alpha polonium is, the structure is beta polonium, which is rhombohedral. Calculate the number of atoms per meter cube for highest electrical conducting material with FCC crystal. We know that the highest conducting material is silver, and it has an FCC lattice with lattice constant 0.408 nanometer. So the way we have to find the number of atoms per meter cube is, we have to find the volume of the cube, and we have to divide by the total volume, so that we get to know what is the number of atoms per unit volume. So after doing that calculation, what you have to do, and we have to remember that in FCC lattice there are 4 atoms in one conventional unit cell. So the number of density is 4 atoms per L cube, and when you put in the value you get 62.8 into 10 to the power 27, which is of the order of 6.28 into 10 to the power 28 atoms. So the correct answer is 10 to the power 28. While the AC impedance, charge transfer and mass transfer are dash, they are in parallel with other electric elements in the equivalent form, and such that mass transfer resistance is domain at lower frequencies than charge transfer resistance at the total resistance of a straight wire, and the measured by varying the frequencies. So as you do this experiment and plot Z real and minus Z imaginary, so at a particular at the particular initial phase, we will be thinking that so at the initial phase, mass transfer is the most dominant form. So mass transfer is the dominant form of frequency uh, at low frequencies. So the way we have to read this plot is shown in the arrow, and the mass transfer region comes, which has low energy, and then the high large transfer resistance will be coming up, which has a low frequency. What will be the average translational kinetic energy for gold metal at 0 Kelvin? So average translational kinetic energy, that depends again on the temperature, half mv square equal to 3 by 2 kBt. So when kBt is equal to 0, then we have half mv square is equal to 0. So there is one more question. CBE is the electronic contribution to the specific heat of solid. It includes the contribution only from free electrons in the solid. So the rest other answers are not so good. So the correct answer is free electron contribution in the solid. So so the question is, the resistance of a conductor, it what happens with, so resistance of the conductor is given as rho L by A, and it is rho L by A. So with increase in the cross section area, the resistance will decrease. So this is your answer. And with increase in its length, the resistance will increase. The conductivity of metallic conductor, so the conductivity is if it uh, the porosity will increase, then the conductivity will decrease. Why? Because there will be now, because of the porosity, there would be the electronic paths that will get hampered. So uh, the conductivity will get decreased. And if there are the presence of precipitates, they are like uh, the electrons which would have which would have been traveling, the scattering time will reduce. So if the scattering time will reduce, sigma equal to n square over m. So sigma is nothing but n e square tau over m. So in presence of precipitate, the tau will reduce. Since this tau will reduce, sigma will also reduce. So it will decrease with the presence of the precipitates. When voltage is applied across a conductor, when voltage applied across a conductor is gradually increased, then when you increase the voltage, then what will happen is the power consumed will, the current will start increasing, because it is a conductor, so sigma will be constant, and when you increase the voltage, the current will also increase linearly, and the power is nothing but V times I, or since V is equal to IR, and R is constant for a given material and of particular dimension, so as you increase voltage, power will increase. So the correct answer is the current will gradually increase and the power consumed will also increase. In an infinitely long metallic wire, if two free electrons are 1 meter apart and the wire is subject to an electric field, then uh, initially both the electrons will initially accelerate, that is true, and even if they are 1 meter apart and they are subject to the electric field, so because of the random motion, they can so they will what will happen here is, when we apply some electric field, this electron will feel the electric field, at the same time this electron will also feel the electric field, so they will initially accelerate, and the electrons can still meet, because even if the acceleration is this side, so there are scattering events happening because of the collision, and so there is a probability that they will meet. In a metallic conductor at room temperature, in the presence of an applied in a metallic conductor in the presence of an applied field, what will happen is that in the presence of an applied field, the average velocity of the electron is not zero, and the average speed of the electron is also not zero, because the electrons anyway, even if there is no electric field, or even if there is field, the speed is never going to be zero, because they are always in thermal motion, and when an applied field is there, then the average velocity will also not be zero. The atomic vibrations are the primary mode of okay. Atomic vibrations are primary mode of heat transfer in all metals at room temperature. So this is false. At room temperature, even the free electrons contribute. The free electrons contribute to the heat transfer as well. The force experienced by the electrons within the solid under the external field is the sum of, it is a positive accelerating force as well as a negative resistive force. The positive accelerating force is that of the electric field, and the negative resistive force is because of the collision with the it is the collision of the electrons with each other which will give rise to a negative force, which is dependent on the velocity of the electrons. calculate the electrical conductivity of a trivalent metal having atomic number. So what we have to do is we have to just follow electrical conductivity. The formula is Nf E square tau over m, and it is a trivalent metal. So we just have to put the value n, put the values. So E square is, so we know what is m, tau and E. So tau is of the order of 10 to the power minus 14 seconds, and E and m are constants. Nf we need to calculate. So Nf, it is, we get to know from this information that if a metal is having an atomic number 13, then aluminium is it is at it has a mass of 27 amu, and 27 amu, and so it's from there we can calculate what is the total number of electrons. So the number of electron per unit volume is 2.7 gram per centimeter cube. This is the density of the aluminium, and the number of atoms is you just have to divide it by its atomic mass, and number of electrons you have to multiply with the valency, which is 3. So on doing that, what you get is Nf, and put that Nf here, and you will get with the required answer, and you will get with this Nf, and after that you will get the required answer. It is of the 1.8 into 10 to the power 29. Okay, so that is your n. This n you have to put back in this formula, and then you will get your required answer. So blower is an essential part of the air conditioner, as it maintains the balance between the warm and the cool by utilizing. So blower, what it will do, it will help in heat conduction, heat transfer by means of the convection process. So this convection process is an important part. So that is why it is essential. Calculate the mean free time of a positive charge of mass. Okay, positive charge it is given, and the mass is given, and the external field has been given, it is 1 volt per meter. So Vf is the Vf is the velocity, and it is E tau over m. It is the drift velocity, and we have to calculate what is tau, and tau is equal to mvf E upon E. So m and E we know what is the value. So Vf upon E that we want to calculate. So E already given, it is 1 volt per meter. We want to calculate what is Vf. To calculate Vf, what we have to do, we have to use this formula. J is equal to the formula for current density. J equal to I times the cross section area, and NEA, so NF EA VF, that is the formula for J. NEA VF and I times A. So VF, it is nothing but I over NFEA. So this A will cancel actually. So here I times A, the A cancels A, you know what is the some text. Yeah. So from here you can calculate what is this VF. From here you can calculate VF equal to IA over NFE, and you can put these values for a typical we can put these values for the typical for a typical conductor, and then you will be able to get what is this tau. It comes of the order of 10 to the power minus 14. This has been done on in the class notes that you can go through, and you can check it out. Two cylindrical rods A and B are made of the same metal having different length, same length but different diameters. Same metal, same length but different diameter. So what will happen is, so R is rho L by A. So same metal means the resistivity is the same. So the resistivity of the same, because it is same metal. Same length, L is same but A is different. So the resistivity will be the same but resistance will be different. A heat exchanger in your laptop is a combination of copper, metal tubes and fans, because one thing is the copper is a good thermal conductor, so it will absorb all the heat by means of conduction, and the fan will blows out and it will bring in the cool air. So that is why it is a combination of copper, metal tube and fans. How does a free electron exchange energy in a solid? So in a solid it will exchange energy by means of collisions, at least in the model of Drude-Lorentz model. Weidmann-Franz law is the ratio of electrical and thermal conductivity, and the Drude-Lorentz model is successful in theoretically predicting this law, because there were two important like happy accident you can say which happened, in which the mean square velocity and the specific heat capacity, they were uh, wrongly estimated, but in such a way that they were compensated by each other. So in Drude-Lorentz model, the heat capacity CVE, it is 100 times the actual value, and the V square, this was 1 by 100 times the actual value, and this both got cancelled in the process, and that is why we obtained that is why Drude-Lorentz model was successful in theoretically predicting the law. When a metal rod is maintained one end at the hot and the other end at the cold, the following are true. The temperature is the function of position. That is true, because the temperature will be gradually increasing along with the position. The energy of the electrons is a function of, so that is also true, because the energy depends on temperature, which depends on the position. The temperature is the function of electron density at that point. So that is not true. It is the function of position only. Energy of the electrons is a function of temperature at approximately the position of the electron is. Yeah, that is true. The energy of the electron is a function of temperature, and it is the function of the temperature is the function of the position of the electron. So in session 4, in a large particle system, dash microstate is probable. So we have seen that different microstates are possible, and amongst the different possible microstate, as we increase the number of particles, then it is only one microstate which has a large number of possibilities, so much so that it is greater than the sum of all other microstates possibilities combined. So that is why it is one microstate which is more probable. That is true. In the second question, in a classical systems, particles are dash in the same microstate. In a classical system, the particles are identical, but they are distinguishable uh, in the same microstates. So the distinguishability is an important factor which differentiates classical system to the quantum systems. Partition function is a function of the partition function is a function of particle density and the energy. So which of this is true? The partition function, it is the function of particle density mostly. The energy of the system, why it is not coming into picture, is because it is subject to the condition that the energy levels of the system may be constant, but the energy of the system is dependent on how these particles are arranged in different energy levels. So it is not the energy, only the particle density. Identical classical particles are distinguishable while quantum particles are indistinguishable. So this indistinguishability is the factor which uh, differentiates quantum and the classical particles. Question number 5 is n I is equal to n by p e to the power. This is known as the Maxwell-Boltzmann statistics, in which it is characterized by e to the power minus ei open kbt. Calculate the electronic contribution to the specific constant value. So it is just put the formula, get the answer type question. So it is the specific heat, electronic contribution to the specific heat in Drude-Lorentz model. It is given by the formula which is same as that kinetic theory, which is 3 by 2 nf kb. Kb is a constant which is 1.38 into 10 to the power minus 23, and nf that you can calculate by the mole theory, and from there you can get what is the specific heat of the copper. And here it has been worked out how do you calculate the nf, and you just have to put in 3 by 2 nf kb, and the correct answer is 1.76 into 10 to the power 6 joule per meter cube. So this is your correct answer. What will be the mean square velocity of the particle in a free gas if the particle mass and the electric charge are 2 times that of electron? So here also you have to put the formula and get the answer. So what you have to find? You have to find the mean square velocity. The working formula is given here in this square box. Half mv square is equal to 3 by 2 kt, and if you are what you are doing is you are increasing the particle mass and the electronic charge, and based on that you put these values, and the answer that you will get is 6.9 into 10 to the power 9, or 69 into 10 to the power 8 meter square per second square. So here it is again the put the formula, get the answer. The formula that you have to remember is V equals to E tau over M, and from there you can get tau equal to Vm over E, and all the values are given, and you just have to put the values. In metallurgical engineering, since the systems are typically molten metals, phase diagrams are usually composition versus temperature plot at particularly 1 atmosphere, because in metallurgical engineering most of the metallic systems are exposed to the atmosphere. So the pressure it is maintained is 1 atmospheric pressure only. The energy levels of a system are identifiable when the system is at energy levels are identifiable or constant when the system is at constant volume. If you change the volume, then the energy levels will start varying. So having that constant volume is essential. A system possessing a total energy 5e has 5 energy states: 0e, e, 2e, 3e and 4e, and it contains 7 particles in it. The number of ways in which the most probable microstate is determined occurs is, so the way we have to solve it is, we have to determine in how many ways this 5e can be obtained with 7 particles and energy levels given as 0e, e, 2e, 3e and 4e. So here we have given the energy levels, so 0e, 1e, 2e, 3 and 4e, and here are the particle distributions. There are 7 particles and all of this you can see 1, 2, 3, 4, 5, 6, 7. So these are the number of ways in which this can be distributed. Now given a particular microstate, so this is a particular microstate. So how you have to do is 7 factorial divided by 0 factorial, 0 factorial, 1 factorial, 3 factorial, 3 factorial. 0 factorial is 1, remember that. So from here we can get for different all of these different arrangements what are the number of ways, and this number of ways we found as 21, 140, 105, 105, 42 and 42. So the correct answer is 140, because that is the most, this is the highest among all this, and the most probable microstate, it occurs in 140 ways. Stirling approximation is ln n factorial, and it is n ln n minus n. It is valid for only large n. Ni equals n by p. So this is p in the denominator is the partition function, and it is the sum over all I. Partition function is given by sum over all I e to the power minus ei over kt. The Drude-Lorentz model does not take into account the Drude-Lorentz model does not take into account the following. It doesn't take into account the influence of ionic cores on free electrons. That is true. It doesn't take into account even the Pauli exclusion principle also. Pauli exclusion principle is taken into account only in the Sommerfeld model. So the answer is all of the above. And the influence of free electrons on each other, that is also not taken into account. So all of the above are true. As the number of particles in a system increase, how many number of microstates become more probable than the remaining microstate? As the number of particles will increase, only one microstate, it will have the more number of ways possible than all other microstates combined. Now we'll discuss the question and answer of session 5. Human body emits infrared radiation just by the virtue of the fact that it is at a constant temperature. So our human body, it is at a temperature of 35 degrees Celsius, and that is why it will be emitting radiation. Classical physics failed to explain the dash because of the quantum mechanical nature of particle. It failed to it couldn't explain how the photoelectric effect is possible. It cannot explain the Compton effect, which and it cannot also explain what are the discrete spectra of atoms and molecules. So these are all of these phenomena cannot be explained by the classical physics. Now here it tells about match the following. So there are different constant: Planck's constant, Stephen Boltzmann constant, the speed of light, and the Boltzmann constant, and we have to match with the corresponding value. The Planck's constant h is 6.626 into 10 to the power minus 34 joule/second, so 1 goes to C. And Stephen Boltzmann constant sigma, it is 5.67 into 10 to the power minus 8, and so you can also guess all this by their dimensions also, even if you don't remember the numerical value. So for example, speed of light, it should have a velocity unit of speed, so it is meter per second. So speed of light, so 3 goes to A. And Boltzmann constant, it is E equal to kBt. E equal to kBt, so you can put in the units of all those, and then you will get to know that the unit will be meter square kg per second square per Kelvin. So Boltzmann constant K is 1.38 into 10 to the power minus 23. Even if you don't remember the numerical values, what you can do is you can find what is the unit and answer accordingly. What is the common between Drude and Drude-Sommerfeld model? Both uses the concept of free electron model, and both assumes that the potential is constant within the solid. Okay, and quantum mechanical properties and Pauli exclusion principle, these are included only by the Drude-Sommerfeld model. The Drude-Sommerfeld model and the Drude model follows the Sommerfeld model follows the Fermi-Dirac distribution, whereas the Drude model follows the Maxwell-Boltzmann distribution. Diffraction phenomena was originally interpreted as the experimental condition for wave-like behavior of the matter. So the answer is false. Sample observes radiation at 530 nanometer and irradiates at 633 nanometer. What is the frequency of oscillators emitting the radiation? The frequency of oscillator, it is simply given by what is the radiated energy. So the radiated wavelength is 633 nanometer. So the frequency you have to calculate is C by lambda, and lambda you have to put for 633 nanometer. The absorption radiation, it can be of any energy, but the oscillator oscillates at its own frequency, which is 633 corresponds to 633 nanometer wavelength. So Rayleigh-Jeans is a law, but it results in ultraviolet catastrophe because it doesn't take into account that. So that was that was the classical model, and in that classical model, the issue was that because there was no discretization, even very small amount of small change in because it doesn't take into account this discretization, even if there is the wavelength is very less. So even if the wavelength is very less, the energy increase was really very high. Whereas it was not the case in case where we have where we need to have a certain discretization. When we have discretization, what happens is the oscillators, they will not all the frequencies will there will be a maximum to that frequency. It is just a result of the quantum mechanical picture of these photons. So Rayleigh-Jeans law suffer from ultraviolet catastrophe, and it is not based on the quantization of energy, and it is not applicable at lower wavelengths. That is true. The red curve that you see in that plot is that of is the result of the quantum mechanical picture. The black body radiation plot between the spectral radiance. It is a plot of the spectral radiance and the wavelength of emitted radiation at temperature T. The temperature of the black body radiation is decreased by 20 degrees Celsius. Then the areas under the power density per unit wavelength, which is your spectral radiance versus the wavelength, the area will decrease because that will give you the total intensity of the. See, if you integrate R with respect to lambda, the area under the curve, that will give you the total intensity, and that total intensity is given by the Stefan-Boltzmann law, sigma T to the power 4. If you decrease the temperature, then intensity will reduce, which denotes that the area under the curve will reduce. A sample absorbs 530 nanometer and irradiates at 633 nanometer. What is the frequency of oscillators? The frequency of oscillators is given by C by lambda, and lambda you have to use of that of the oscillator. So that will give you around some petahertz. A graphite die is heated at 1200 degrees Celsius for 30 minutes and then immediately kept in a location that is room temperature. So it is now equivalent to a black body, because graphite, uh, it will display a radiation of energy by virtue of the fact that it is at a very high temperature. Two samples A and B are at temperature 25 degrees Celsius and 100 degrees Celsius respectively, kept in a dark room. Calculate the peak radiation wavelengths for sample A and B. So for 25 degrees, so you have to use something called Wien's displacement law, which is given here. Lambda max times T, lambda max times T is 2898 micrometer Kelvin. So you just put in the value of temperature in Kelvin. So you have to remember that this 25 degrees Celsius and 100 degrees Celsius, that you have to convert it back to Kelvin, and then you have to use this formula, and from there you will get the corresponding lambda max. And here they have been calculated, and it is 9.7 micrometer and 7.8 micrometer. In quantum mechanics, counting the microstates are impacted by it is impacted by what if the electrons are identical or indistinguishable, and and we have to need to use the Fermi-Dirac statistics. And yeah, and in quantum mechanics, the electrons are the distinguishable nature of electrons. So this is false, because electrons are not distinguishable, they are indistinguishable. Protons and electrons differ from each other because of proton has a different mass, different charge, as well as different size. So they are totally different, but they have same spin. Both are half spin particles. Calculate the approximate intensity of black body radiation. That intensity you can again calculate by Stefan Boltzmann law, which is I of t is given as sigma t to the power 4, and if you just calculate that, you will get the required value. Calculate the approx intensity of black body heated at 4727 degrees Celsius. The intensity of a black body, so again this can be calculated by Stefan Boltzmann law. Match the following. So Max Planck, so these are some scientists, physicists, and what are their findings. So Max Planck used the Max Planck is known for the quantization of light, and the fact that quantization of energy. Lee de Broglie, he told about the wave particle duality, and Erwin Schrödinger gave the he gave the wave equation. Max Born interpreted the wave function, and Werner Heisenberg told about the uncertainty principle, and Albert Einstein, he actually demonstrated in photoelectric effect how light can be treated as a particle. In session 6, if a system is under thermal equilibrium, in case of Fermi-Dirac distribution, it assumes that the system has constant total energy, the system has constant number of particles, and the change in total energy and the total number of particles remains 0. So these are your constants to which during the derivation of Fermi-Dirac statistics, these are the constants under which the system was subjected to. The system has varying energy but constant temperature. This is not true. And the third point, that change in total energy and the total number of particles is 0, is a consequence of the first two statements. If the total energy of a closed system is constant, that means the number of particles keeps on increasing. That is not true. The product of total energy and the number of particles at each energy remains constant. So that is not true, because the energy levels can be it is not the product of the number of particles. So it is not, it is the sum of the total number of particles at each energy level is same, and the change in energy will be 0. Yeah, that is true, because it is constant. The system is being heated steadily. That is not true, because the system is at a constant temperature. In Fermi-Dirac distribution, f of EI is 1 when so again you look at this figure, the red color plot, it tells you at what happens at t equal to 0, and the green plot it tells you what happens at t greater than 0. At t equal to 0, what is happening is, for all the energies which is less than EF, you have f of E is 1, and for t which tends to at t approximately equal to 0, the energy has to be less than EF. So the first and the third options are correct. The probability of occupancy of states of fermions in a solid at temperature greater than absolute 0 is f of E I is 1 always. That is false, because there is after EF, when your energy is greater than EF, you don't have this uh, uh, yeah, you have the occupancy probability will be 0. So it is not always. The third option is correct. Again, you can infer from this plot. The Fermi-Dirac distribution f of Ei becomes half when your energy is at exactly equal to the Fermi energy and the temperature is greater than 0 Kelvin. The probability of occupancy of states of fermions at solid at temperatures greater than 0, this we have discussed just now. A system containing energies E1, E2 have this many states. So the number of states and the number of particles have been given. In how many different ways can you arrange empty states alone in energy level E3? So energy level E3, we have 9 states and 3 particles. Then the number of empty states is 6, and the number of ways 6 states can be arranged is 6 factorial. So the correct answer is 720, which is 6 factorial. What is the maximum number of arrangements possible in the energy level E3 in question 1? So maximum number of arrangements possible in E3 is, so you have 9 states and 3 particles. So out of 9 you have to choose 3, and that can be done in 9 choose 3 ways. So if you do 9C3, then the correct answer that you will get is 84. What is the conditional probability that the energy level E3 is occupied? And so the conditional probability is NS, so Ni by Si. For 3 it is N3 by S3, it is 3 by 9, and it is therefore it is 1 by 3. The most probable arrangement is significantly larger than the next term, and it is significantly larger than the sum of all the term. Yeah, that is true, and it is really very very large, and so large that it is almost considered to be equal to 100% or 1. So the first 3 options are correct, and majority and therefore considered to be 51%. This is not correct, because it is majority and it is of the order of almost equal to 1 or 100%. Match the following. T at absolute 0. So this is again a statement about the Fermi-Dirac statistics. From the plot you can infer that when t equal to 0, f of E equal to 0, exactly 0 when E is greater than EF. So the option A goes with 3, and at t greater than 0, f of E is equal to half when E equal to EF. So B goes with 4. The probability of occupancy f of E versus energy E plot of the Fermi-Dirac distribution at absolute temperature has all the information about so it has the information about the number of states occupied by the electrons and the density of, so it has the information about what are the energies that is occupied by the electrons, and it has the information of what is the highest energy level occupied by the electrons. So here in the question you see it has told you what is the information except, since it has told except, you have to give the correct answer would be the information which is not given by the Fermi-Dirac distribution, and the density of allowed states and number of electrons are the ones which are not given by this Fermi-Dirac distribution. For that you have to know something called the dispersion relation. Without that you cannot find what are the number of states and the density of allowed states. F of E at the Fermi energy of collection F E at the Fermi energy of collection of fermions in a solid at temperature minus 270 degrees Celsius is, so it is minus 270 degrees Celsius is just 3 Kelvin. Since it is 3 Kelvin, it is T is greater than 0, and since it is T is greater than 0, you can see from the plot you have to follow the green plot, and so it has to be less than 1. It cannot be equal to 1. At T equal to 0 or exactly minus 273 Celsius, it would have been equal to 1, but in reality it is less than 1. Which anomaly of Drude-Lorentz model was corrected by the applying Fermi-Dirac distribution? Yeah, so there was this anomaly of heat capacity, contribution of electronic heat capacity by the electrons, and it was off by a factor of 100, and since it was off by a factor of 100, the use of Fermi-Dirac distribution rectified the anomaly. In the classical Drude model, only few particles participate in gaining energy on increasing temperature. This is the fundamental reason behind the failure of Drude model. This is false because it is not the classical Drude model. It is the Sommerfeld model, in which only a few particles will participate in gaining energy. So instead of since it is the classical Drude model, it has been given, it is false. Had it been the Sommerfeld model, then it would have been true. The Drude-Sommerfeld model is successful because it assumes electrons are fermions, that is correct. It assumes all the particles are identical, that is true, because fermions are quantum particles and quantum particles are identical as well as indistinguishable. It assumes that the fermions of the solid participate in the process. No, all the fermions doesn't participate. In this slide you can see that shaded green region, only those electrons will participate in the process of gaining energy, and they are actually very small number in quantity. So only a very few fermions will participate in the process of gaining energy, that is true. So here are the question and answer of session 7. So dash shows a perfect atomic orientation and different properties in different directions. So a single crystal shows perfect atomic orientation and different properties in different directions by virtue of difference in the periodicity when you look at different directions. Polycrystals are much smaller in size, and randomly oriented crystals have, so since they are randomly oriented, they will have isotropic properties, whereas graphene is highly oriented material and it will show an isotropic property, such as the conductivity on one of the plane is very high, whereas the conductivity in the other direction is really less. Potential energy of a free electron approaching towards the ionic core dash. Yeah, potential of a free electron approaching to, so it is just an attraction of positive and negative particle. A positive particle, so you just have to remember this plot. So there is this plus and minus. When they will come closer, it is 1 minus 1 by 4 pi epsilon naught 1 by r square. So and there is some z square based on the charge. What is the charge? Okay. So as they approach, it will go towards, it will keep decreasing. If you plot this with respect to r, it will be like this. This is going towards 0. At infinity it becomes 0, and here the potential energy of the free electron towards ionic core, this will decrease. In a meter long solid, the nearly free electrons are dash and bound electrons are dash. In a meter, the nearly free electrons are free to run across the solid and they are confined, whereas the bound electrons are confined to the ionic cores. And since it is a meter long solid, they are free to move within the 1 meter distance, the nearly free electrons, whereas the bound electrons are confined to only to a very few angstroms. The table shows below the condition and a result due to a condition. Shows a condition and the result due to the condition. Based on this, pick the correct choices. Okay. The condition that it is a truly free electron. If it is a truly free electron, then there has to be no restriction on lambda that can be supported. That is true. So condition A, A is true. The electron confined in a potential well and any discrete set of, no, as long as the electron is confined in a potential well, it is not any discrete set of lambda. It is a very specific set of lambda can be supported based on the energies that is given by the quantum mechanics, the Schrodinger equation. So when you solve the Schrodinger equation for that potential well, you will get very particular values of k values, and for that k values there are very specific values of lambda. So it is not any discrete set of lambda, but it is very specific set of lambda, which are the eigen lambda values or the eigen energy values. So B is false. A potential well in a material, it can be very deep at specific locations, that is true, and it is of the dimension, and the depth depends on how strong is the electronic or the electrostatic attraction is. It is of the atomic dimensions at some locations, that is true. At the location of the presence of ionic cores, it is of the dimension of ionic atomic dimensions. It is a representation of potential energy experienced by an electron under the influence of ionic cores of the solid. That is also true, and it is different for a free electron and a nearly free electron. That is also true. For a nearly free electron, it is bound within 1 meter of a dimension of the 1 meter or within the dimension of the metal, whereas a truly free electron, it can roam around freely. The length scale of freedom of an electron participating in the photoelectric effect is not same as, yeah, the length scale of electron participating in photoelectric effect, that electron are nearly free electrons, whereas the bound and trapped electrons, their length scale of freedom is few angstroms, and but nearly free electrons, they have a length scale of around 1 meter of the length of the entire metal. So this is a true statement. The value of work functions of a material is, the value of work function of the material, it is a positive value because it is given by the, what is the vacuum energy minus the Fermi energy. In a solid, energy of an electron is not continuous when it is free to move within dash distance range. The energy of an electron is not continuous when it is free to move within, so it will not be continuous when we have a discretization. The discretization, the only condition is, so all the first three conditions, they are not totally confined, whereas the fourth condition, it is confined from 0 to 2a, and a is in angstrom. So this is in this distance range, the energy of the electron is not continuous because of this confinement. The Schrodinger wave equation consists of kinetic energy as well as the potential energy terms. It is true. The single crystal, when compared with a polycrystal of small grain size for the same material and phase, it is more likely to display anisotropy, because on different directions you will see different periodicity of atoms, and it will have the crystal structure throughout the sample just like the polycrystal sample. The only difference is that there are no small there will be no grain boundaries, but the crystal structure will be the same as that of the polycrystal. The graphene displays anisotropy because because of its crystal structure. It is the crystal structure that actually is that will give rise to this anisotropies. The electron, which was earlier confined to 0.2 nanometer, is later freely moving in 1 meter of space, and after a certain time under this motion, it suddenly has no confinement at all. Based on these observations, the energy of the electron is continuously increasing. So you have to remember this particular plot of, so this is the free region and these are the atomic wells. So an electron which was earlier confined to 0.2 nanometer, these are the dimensions of atomic dimensions. So this is like 0.2 nanometer, whereas this dimension is of the order of around 1 meter. So if its energy start increasing at certain level, this will become the energy level, which is the nearly free electron energy level, and then if you increase further, it will become totally free. So you see that energy is continuously increasing. The energy spacing level is also decreasing. So that is, A is true. The energy spacing is, so here the energy spacing, when it is very very confined, the spacing would be of the order of a few electron volts. When it is nearly free electrons, the spacing is of the order of so 10 to the power minus 9 electron volts, and when it is totally free, there is no energy spacing at all. So it keeps decreasing with the passage of time. That is true. When only one end of the string is tied, the wave of any wavelength can move on it, but when both ends of the string are tied, the wave has some restriction imposed on the wavelength. Does it hold true for practical example of violin strings around 20 to 30 centimeters? Yes, that is true, because both of the ends are tied, and since both of the ends are tied, only certain standing waves are possible in that string. The anisotropy of a material, it is due to the periodic arrangement of atoms, and it enforces the electrons to feel the different potential at different locations just by virtue of this anisotropy. That is true. And it doesn't depend on the size, and it is not a result of the magnitude of the properties in different directions. It doesn't result in same magnitude. In different direction, it results in different magnitude of the properties. Now in session 8, the Fermi surface in 3D K space is spherical, because if you see this formula, 2me over h bar square equal to the k square ky square plus kz square, this is the formula of a sphere, and it is a three-dimensional surface. It is surface in 3 dimensions because sphere is a 3D object. The relation between the Fermi energy and Fermi temperature is, the Fermi energy is it is related by EF equal to kBT, so it is linear. The Drude model overpredicts the electron. So the Drude model, it overpredicts by a factor of 10 to the power minus 2. It is 100. So what you have to remember is, it is 100 times the actual value. The relation between dE and E and the total number of occupied states is parabolic, because d of E goes as e to the power half. As the material temperature increased, only electrons closer to the Fermi energy are able to participate in the specified process. Those which are inside, they cannot participate because there are the energy levels filled just immediately next to them. The density of allowed states for an electron in a metal is so more at the Fermi energy, then so you see it is increasing. The density of allowed states is increasing with respect to E as e to the power half. So it increases with increase in energy, and it is independent of the density of occupied states, because density of occupied states is given by n of E, which is a product of f of E and dE. So these are two independent quantities, so it has nothing to do with that, and it is not dependent on the probability of occupancy either. Probability of occupancy is f of E, that depends only on the Fermi energy and temperature. According to the Sommerfeld model, the free electron contribution to specific heat at constant volume is less than the that of the Drude model. In classical Drude model, what happens is all the electrons were contributing to the specific heat, but here only the electrons nearer to the Fermi energy will be contributing, and it is impacted by the Fermi temperature of the material, because Fermi temperature is related to the Fermi energy, and that will determine at what temperature the material at what is the uh, specific heat depends on that, because that will tell you how many number of electrons actually participate in this heat capacity process. The first two options are not correct, because it is neither equal to nor greater than, it is actually less than that of Drude model. A system comprised of two materials A and B is kept at room temperature under constant pressure. The chemical potential of the electrons in the system, so when A and B are brought together in contact, so the chemical potential will average out and the net chemical potential will be the same, and there will be no flow of electrons happening between A and B, so it is the average. Now the wave vector corresponding to the Fermi surface of a metal at 0 Kelvin, uh, it corresponds to the longest wavelengths permitted, so that is wrong. The at Fermi surface is actually your highest energy, or the EF. So highest energy means lowest wavelength, so it corresponds to the shortest wavelengths of permitted electrons, and that corresponds to the largest magnitude of wave vector, because shortest wavelength means largest wave vector. The Drude-Sommerfeld model says that dash participates in the process gain of energy on increasing temperature. Only your nearly free electrons, or the electrons near your Fermi energy, only those electrons will participate. The classical Drude model overpredicts the electronic contribution to the specific heat at constant volume. This is true. Two metals A and B have Fermi energies 1 electron volt and 2 electron volt. Which of the two are definitely true about these materials? So B has, so atomic number has nothing to do with it, neither the density, and so B has more free electrons per unit volume than A. The density of free electrons, it has to do with the Fermi energies, because the Fermi energy is related to the density of free electrons as 3 pi square n to the power 2 by 3. So B has more free electrons because it has more Fermi energy. Which property of electrons help in studying the periodicity of the lattice inside a material? It is the wave particle duality. It helps us to the study of electrons and in the study of so that's when for example electron diffraction is happening. So electron diffraction, so there is something called SAE, selected area electron diffraction from a particle. So this electron diffraction, it helps there the electron is treated as a wave, and that wave particle that wave nature helps us to determine the periodicity of the lattice inside the material. That has to be of the order of lambda f. In the Sommerfeld model, the number of electrons per unit volume can participate in the process of raising the temperature of a material, and it is just dF times kBT. dF is given by 3 by 2 NF by EF, and kBT is the increase of the temperature. So when you just see, that is the correct option. The wave function value for a deep potential well of length A is 0 at x equal to A, and 0 at x equal to 0, and 0 at x equal to A. These are the boundary conditions. And it cannot be 1, so it has to be 0 at the ends particularly. What is the main difference between a real and a reciprocal lattice? So both have unit of the length, so that is false. Real lattice is a unit of L and reciprocal lattice is unit of L inverse. For some crystal structures, the representation in reciprocal lattice is different from that of the real lattice. Uh, that is true, because the representation in reciprocal lattice can be BCC, but in the real lattice is FCC, means reciprocal lattice is BCC. So the representation may be different. The reciprocal space is a representation of real space in a different framework. That is also true, because given all the unit vectors in the real space, you can determine what are the unit vectors of the reciprocal space. When correlating real space with reciprocal space, what can be replaced at the question mark given below? So the question mark, you see, it is like it is in the direction of the cross product of A1 and A2, and the cross product of A1 and A2, it is given by B3. So B3 is proportional to this cross product, so the correct option is B3. So the third question, it is A vector, B vector and C vector are the lattice vectors in the real space, and if n is the unit vector given by this value nb h b2 and l b3, then what will be the vector product of the unit vector a1 by h? So a1 by h is nothing but your o a, and it is given by this dhkl, and that denotes your interplanar spacing. And a1 by h is you see along this a1 vector, this oa is your a1 by h. Okay, so that represents your intersection of that is actually the intersection of uh, the plane ABC with that of this unit vectors, and this plane ABC is the plane in which atoms are arranged. Let us assume A vector, B vector and C vector, and B1, B2, B3 are the real and reciprocal lattice vector. What will be the volume of, so here you can just calculate what is the volume of BCC lattice and the FCC lattice given by this formula written here for A1, A2 and A3. The diffraction condition in just a minute. The diffraction condition in real space and reciprocal space are given by, so it is given by the Bragg's law and Ewald sphere construction, and Bragg's law is given as 2d sin theta equal to n lambda, and the formula that you see, s by lambda minus s naught by lambda equal to hb1 plus kb2 plus lb3. This is the representation of your Ewald sphere construction. What causes directionality in a solid? It is the crystal structure that causes directionality in the solid. Reciprocal space describes the interaction between dash in greater detail than real space. So it is the crystal structure and waves that the reciprocal space describes in a greater detail. The magnitude of HKL in reciprocal space is 1 by dHKL. According to Bragg's law, the total path difference 2d sin theta should be an integral multiple of lambda for the constructive interference. So the correct answer is wavelength. The equation S by S naught in reciprocal space contains the properties of all waves which are arriving or leaving at or from the lattice. So it is, if you see the Ewald sphere construction, then it will be more clear to you. So the correct answer is arriving and leaving. A three-dimensional sphere in reciprocal space known as Ewald sphere corresponding to a single wavelength, it satisfies diffraction conditions wherever the surface of the sphere will touch the reciprocal lattice points. So whenever so the diffraction condition is satisfied when surface of evolved sphere is touching the reciprocal lattice point. So it is the correct answer will be the surface. A simple cubic lattice in a real space when compared with its representation in reciprocal space is such that dash is or origin a simple such that no angles are changed, because in reciprocal space also it will still remain a cube, so angles will not change. The abscissa lattice, the face centered lattice in real space is represented by a body centered lattice in reciprocal space. This is true. FCC is represented by VCC in reciprocal, and real VCC is represented by reciprocal FCC. If white radiation, meaning a wide range of wavelengths between a lower wavelength and a higher wavelength, is used to probe a crystal, this is represented entirely in the evolved sphere notation. So now we have a range of wavelength. Since we have a range of wavelength, the evolved sphere will be now a continuous series of spheres with varying radii from that lower wavelength to the higher wavelength. Now the live session 10. Okay. The the Wigner seed cell is a region in the uh, the Wigner seed cell is a region in the space which is closest or nearest to the given lattice point than to any other lattice points. So the correct answer is closest and nearest. The Bragg plane is the perpendicular bisector to the line joining the origin of the reciprocal space to any reciprocal point, and the first Brillouin zone can be defined as, so it is the first Wigner seed cell about a reciprocal lattice point in the space. The region before crossing any Bragg plane in any direction, it is an equivalent statement, and the region in space that can be reached from origin without crossing a single Bragg plane, and the region that is a subset. So this is also true, because the Wigner seed cell is the subset of the region which is enclosed by the second Bragg plane in all directions. So that is also true. The reduced zone scheme is based on the first Brillouin zone only. So if you have the first Brillouin zone, there all the EK values you will get to know. Wherever the diffraction condition is satisfied or diffraction occurs, certain values of energies are forbidden. So you see that in that red diagram there is an opening of the energy values, and the energies are also actually discontinuous, because even if it looks continuous, so there is a very small spacing between these energy values. The Wigner seed cell will be dash-sided figure for a 2D lattice which is other than square and rectangle. It will be a 6-sided figure. So as you can see in this plot, the first Brillouin zone is a the first Brillouin zone is a dash about so it is a first Wigner seed cell about a lattice point in the reciprocal space. A Brillouin zone is always continuous. This is false. A Brillouin zone, it becomes so it is discontinuous because it has the discrete k vectors. The diffraction phenomena occurs whenever so in the evolved sphere construction you will, so the first is the condition of the evolved sphere, and the wave vector will touch the Bragg planes. When this happens, the diffraction will happen, and the wave vector touches the Bragg Brillou's zone boundaries. The Brillou's zone boundaries are nothing but your Bragg planes only, and one end of the wave vector touches the Ewald sphere. So that is true. What is the information that can be extracted from the image given below? Here the reciprocal lattice point positions, that is so that can be extracted. How we can extract that? So wherever there is discontinuity of the energy, that discontinuity of the energy, if you double that value, then you will get the reciprocal lattice point positions. The energy of the wave vector that we can get, because the y-axis is the energy. The allowed and forbidden gaps, that also we know from the right hand side picture, where uh, where certain flat band diagram is given. And the position where diffraction condition is satisfied, that is also we know, wherever the k is a multiple of pi by a, that also we know. So all the options are true. Let us assume that a material of length L has a bound electron zone of length m. What will happen when we plot both of them on the same scale? uh, yeah, so you see the energy levels of free and bound electrons. On the denominator we have L square and for free electrons, and on the denominator we have m square for the bound electrons. So the energy level of free electrons are more closely spaced than that of the bound electrons. That is true, because if you see compare the length scale, then you will get to know that how closely they are spaced. The energy levels of free electrons are higher in energy than uh, higher in energy than those of the bound electrons. This is also true. Dash represents the value, the details of E versus K relationship at. So it is the reduced zone scheme, extended zone scheme, and the repeated zone scheme. All these three are equivalent representations of the band diagram. A slice of Wigner seed cell passing through the body center and parallel to 100 plane. So if you just cut that, you will get an octahedron. A semiconductor component based circuit might fail in spacecraft. So yeah, pressure has a very significant role in determining what is the interatomic spacing, and that interatomic spacing has a role in determining what is the band gap. So what we might be thinking, a semiconductor might be an insulator or a metal at a different pressure. So semiconductor component based circuit might fail because of high pressure, because it may not behave as a semiconductor. If the band gaps are considered at three different atomic distances, x1, x2, x3, where x1 is smaller, x2 is smaller, and x1 smaller than x2, smaller than x3, the relative band gaps will be such that you see here x1, x2, and x3, and determine what is the band gap. The band gap at x2 is given by this black line, this black double arrowed point, double arrow lines. So band gap at x2 is wider than x1 but narrower than x3. So that is the correct option. A free electron approximation and tight bending approximation lead to the same result but are originated based on different concept. The latter concept is based on the strong atomic bonding, and that is why it is not so relevant for metallic system. In metallic system, free electron would have been more relevant. The charge carrier concentration versus temperature plot consists of dash regions, and okay, for intrinsic it consists of only one region, and for extrinsic it consists of three regions. One is freeze out, extrinsic, and intrinsic region. Using the chronic Penne model with a finite square wave potential system, dash are the parameters which will vary even after fixing the physical crystal structure. The alpha and beta, they involve the energy term, whereas the system constants like V naught, the periodicity, the A and the B and B, these are fixed once the dimension of your potential is fixed. The Bloch's theorem discusses about the wave function at lattice position and x plus a. That is true, and the Bloch's theorem gives psi of x plus a is psi of x e to the power ika. Doping an initially intrinsic semiconductor with a p-type dopant, the Fermi energy will actually reduce. It will be near the valency band, so it lowers, and since it lowers, it basically shifts. The tight binding approximation differs from the free electron approximation in its approach because the former in the former the electrons are bound to each atom and the atoms are brought closer to determine the effects of the formation of the solid. So let us assume that the in the material three energy levels E1, E2, E3 have different energies, E1 less than E2 less than E3. What is the sequence of energy level splitting? So the splitting will happen first, the higher energy level will split, then the inner just lower energy level will split, then the further inner energy level will split. So the sequence is E3, E2 and E1. In the free electron theory, this is explained or investigated using equilibrium atomic spacing. So the bandwidth and band gap, it is explained by the equilibrium atomic spacing. The band gap width increases with that will increase with your decrease in temperature, decrease in pressure and increase in atomic spacing. The free electron approximation addresses the existence of anisotropy based on different locations of the Brillouin zone in different lattice direction. So that is the correct answer. In which material less conductivity at room temperature but has less conductivity? See, silicon and gallium arsenide, these are your semiconductor, and semiconductors, if you increase the temperature of semiconductor, then their conductivity will increase. Whereas iron and copper, they are metal, and if you increase the temperature, then their conductivity will decrease. What happens if the energy of the electromagnetic radiation incident on a material is lower than the band gap? So if the energy of electromagnetic radiation is lower, then it will not get absorbed and the material will be transparent to the electromagnetic radiation. So what is common between MRI and particle accelerators? So the presence of superconductors, and since superconductors are formed because of the presence of Cooper pair, so the common thing is in these two technologies, superconductors and Cooper pairs. Superconducting state to normal state transition is gradual in type 2 superconductors and it is abrupt in type 1 superconductors. The Cooper pairs can form when electrons are several nanometers apart, and they will interact through lattice spacing or the phonons. Match the following. Photons are the particles of light. Phonons are the particles of sound. Cooper pairs have zero integer spin, and Higgs particle is a boson. The superconducting state of a material is decided by three parameters, and it is decided by what is the magnetic field, what is the temperature, and what is the current density. So there are critical values to all these physical quantities, beyond which the superconducting state will become non-existent and it will become a normal state. Dash in a material is indicated by a weak opposition to an. So the diamagnetism is the phenomena which is characterized by the weak opposition to the magnetic field, and the diamagnetic susceptibility is of the order of 10 to the power minus 6. A material which shows magnetism only in presence of external magnetic field are called non-magnetic materials, and non-magnetic materials are particularly the paramagnets and diamagnets. A dash structure causes the change in, so the electronic structures causes the change in the crystal structure for specific values of E by A ratio, and so the different crystal phases are the different Humer-Ruthrie phases. So the correct answer is electronic and crystal. Phonons are nothing but your quantum of lattice vibrations, and lattice vibrations, they form nothing but, so they are also called your matter waves. An optoelectronic device is preferably made of a direct band gap semiconductor, because a direct band gap transition, material with direct band gap transition will involve only photons, and because they are only photons, they are more likely to interact with the photons than an indirect band gap semiconductor. The low temperature superconductivity is explained using something called BCS theory, and the BCS theory that proposes something called Cooper pair, and Cooper pair has integral spins. Integral spin particles follow Bose-Einstein statistics, and since they have integral spin, so it can be explained without having Pauli's exclusion principle. So they don't follow, bosons don't follow Pauli's exclusion principle. So the quantum statistics excluding Pauli's exclusion principle is the correct answer. The high magnetic field can break and oppose the superconducting behavior, because the magnetic field, it will try to align the spin of the electrons in the same direction, but superconductor need to have something called Cooper pair, and that in the Cooper pair the spin of the electrons need to be opposite. And magnetic field also, this whenever you have this superconducting phase, they will not allow any magnetic field to pass through it, so they're perfect diamagnet, and this is called Mesnier effect. So this Mesnier effect will also be tried to opposed in the presence of a magnetic field. So Cooper pair interaction through lattice using phonons at a distance of approx a few nanometers makes it a relatively long range phenomena. Yeah, so Cooper pair, the two electrons in the Cooper pair, they can be nanometers apart, and they interact with each other by the phonon coupling. Among the type 1 and type 2 superconductors, type 2 is more preferable because because type 2 superconductor can be present at relatively higher temperatures, and it has two critical magnetic fields, and the two critical magnetic fields, in between the two critical magnetic fields there is something called a mixed state, in which different patches of superconductivity can be there. So one needs a higher magnitude of magnetic field and relatively higher temperatures to uh, because they can handle higher temperatures and higher magnetic fields. Cooper pair formation requires two individual electrons with opposite spin, opposite wave vectors. So these are the two correct options, and if in case the question comes, they need to also have to interact via a phonon. So thank you so much. So this is all about the revision of the questions in the last 12 weeks. Thank you so much.